Now, for general functions, continuity can be quite tricky to show, but there's one case in which it turns out to be relatively simple, and that is in the case of linear maps, which we've already met. In this case, we get a pretty remarkable result that continuity is equivalent to a uniform boundedness condition. So in some sense, our linear map is bounded. We will see in what sense that is. And in actual fact, it gets even more remarkable that we only require continuity at a single point, and that implies continuity everywhere. So we actually have a three-way equivalence. Continuity is equivalent to continuity at a single value of the input, which is equivalent to a uniform boundedness. So this is the actual result which we're going to prove. Let's say that we have norm spaces X and Y. So what do I mean by a norm space? I mean X and Y are vector spaces. Right? First and foremost, they are vector spaces. So they have a vector space structure. Additionally, on each of these spaces, we can define a norm. So on here, I can define a norm. Let me write it like this, which measures the size of any vector X in X. Now, when I say measures the size, I mean it is a measure of the size. It's not a unique measure of the size. It's the way that we are choosing to measure the size. And similarly, we have a way of measuring the sizes of vectors Y in this vector space Y. So this is for any Y in Y. So we have norm spaces. Now let's take any linear map. So if you recall, linear maps T are maps such that the following is true. So T acting on X plus Y is equal to T acting on X plus T acting on Y. That's the first condition. Second condition is that T acting on a number times X is the same as that number times T acting on X. So these are the two conditions that define linearity. And the set of all maps T such that X maps to Y, vector space X maps to so elements of X map to elements of Y, such that T is linear in this sense. The set of all of these we denote like this, hom X, Y. So what does this mean? This is a set of homomorphisms between vector spaces X and Y. So homomorphisms are structure preserving maps, and in the case of maps between vector spaces, these coincide with linear maps. Now, we're also assuming that X and Y are, in this case, we'll keep them finite dimensional. We won't look at infinite dimensional cases, although it doesn't make any difference in this case, actually. Now, if we have a linear map, it turns out that it is continuous if and only if the following condition holds. That the size of the mapped point T x, so T of x, is less than or equal to some number m, which is positive, times the norm of x. So there is some m such that this is true for all x. So this holds for all x in the vector space X. So this is the result. And in actual fact, we can go one step further. We only need continuity at a single point, say at the point 0. So what I'm saying here is that actually continuity for these sorts of maps, these linear maps, is equivalent to continuity at just one point. And we can pick any point. And conventionally, we would pick the point 0. So that is, if T is continuous at 0, what I'm saying means that it's continuous everywhere. So why is this? Well, let's remind ourselves of what continuity means. So in the case of, let's use the sequential definition of continuity. which we can because we have a norm space, so it's metric space and therefore it's first countable. And that's equivalent to the epsilon delta and the topological definitions. The definition of continuity at a point x is that if we have a sequence xn converging to x, then this implies that xn converges to t of x. Or if xn minus x, the norm of this difference converges to 0, then the norm of this difference minus t of x also converges to 0. So this implies this. Now, at the point 0, so if you want to show continuity at x equals 0, we need a sequence xn converging to 0, implying that xn minus t0 converges to 0. Well, t0 is 0, right? T of 0 is 0 because t of 0 can be written as t of 0 times any vector v, which by our linearity properties is 0 times t of v, which is 0. Right? So t of 0 is 0. So what we're saying is that if the norm of xn converges to 0, this must imply that the norm of t of xn minus 0 converges to 0. So this is the condition that we require for continuity at 0. This is the general condition. Now, why is this the case? The continuity at 0 implies continuity everywhere. It's simply from this linearity property. So if you go back to what I just said, we have this property that t of x prime minus t of x is t of x prime minus x. And so the norm of this is equal to the norm of this. So we need to show that if xn converges to x, t of xn converges to t of x, or xn minus x converging to 0 implies the norm of t of xn minus t of x converges to 0. But this is the same as t of xn minus x converging to 0. Now let me define Zn is xn minus x. Then what is this? It's saying that if Zn, which lies in x, because both of these lie in x, so Zn itself will lie in x, Zn converges to 0, this, then we must have t of Zn converging to 0. But this is exactly the condition we require for continuity at 0. So by essentially using this linearity property, we can show very simply that continuity at any point is equivalent to continuity at 0. So if it's continuous at 0, it's continuous everywhere. So we're going to start out by showing that continuity at 0 of t implies uniform boundedness. So let's remind ourselves of continuity using the epsilon delta definition, because that's the definition we're going to use. So the epsilon delta definition of the continuity of t at x, so we want t continuous at x, is as follows. T is continuous at x. Let me actually put x star. T is continuous at a point x equals x star if for any epsilon greater than 0, there exists a delta greater than 0 such that the norm of x minus x star less than delta implies the norm of t of x minus t of x star is less than epsilon. So what is this saying? It's saying that for any epsilon positive. Whatever value we choose, however small or however big, we can find a number delta, which is also positive, such that if x belonging to x is within a distance delta of x star, then t of x is within a distance epsilon of t of x star. And if this holds, then we say t is continuous at x star. And this is the so-called epsilon delta definition. Now, what happens at 0? Well, we'll just put x star equals 0. And we get the norm of x less than delta implies the norm of t of x is less than epsilon. Now, we can do this for any value of epsilon, as I said. So we can choose epsilon equals 1. So we would get this. We need this implying this. This has to be true if t is continuous at 0. So let me state that now cleanly. If t is continuous at 0, then there exists a delta greater than 0 such that x, norm of x less than or equal to delta implies norm of t of x less than or equal to 1. We can use less than or less than or equal to. Both are fine as definitions. Now, let's take any non-zero vector x in our vector space x, and let me define this number lambda as delta divided by the norm of x. Then the norm of lambda x is equal to delta. Now let's use linearity. So using linearity, we have that t of this number lambda times x has to be equal to lambda times t of x. Now let's take the norm of both sides of this. So the norm of this has to be equal to the norm of this. Well, that's just a number, which is positive, so we can take it outside. So this is equal to lambda times the norm of t of x. Now, we have the following condition. We are assuming continuity at 0 using the epsilon delta definition. So that says that if the norm of, let me say, x prime is less than delta, this implies that the norm of t of x prime is less than 1. So this is true for any x prime less than delta, less than or equal to delta. Now, lambda x has norm equal to delta. So it satisfies this condition, and therefore the norm of t of lambda x has to be less than or equal to 1, right? Which is the second condition. And this is equal to lambda times t of x by linearity. And so from here, what do we get? By very simple algebra, we get the norm of t of x is less than or equal to 1 divided by lambda. But what's lambda? It's delta divided by the norm of x. So the norm of t of x is less than or equal to the norm of x divided by delta. So let's just set m equals 1 over delta, and then we get this condition. And this is true for all x, because as I said up here, for any non-zero vector, this is true, right? The boundedness obviously holds for the vector 0, right? It's 0, so it's bounded. So that's trivial. So we only need to consider non-zero vectors. And if it's non-zero, then we can divide by the norm of x, because the norm will not be 0. So we've shown that continuity at 0 implies our uniform boundedness. Now let's go the other way around. So we want to show, this one is a bit easier, we'll show that boundedness leads to continuity at 0, which, as we know, means continuity everywhere. So let's now assume the boundedness condition. Then what? Then the norm of x prime minus x less than delta implies that t at x prime minus t of x is less than or equal to m times the norm of x minus x prime. Why is that? That's from linearity, because this is equal to the norm of t of x prime minus x. By linearity, this is equal to this, right? And from this condition here, that tells us that this is less than or equal to m times the norm of x prime minus x, right? Which is exactly what I've written here. which is less than m times delta, right? From here. So if that's less than delta, then this has to be less than m times delta. So just choose delta equals epsilon over m, and we have continuity at 0. And that's it. Let me be a bit more explicit. Let me call this x prime minus x like I did before. Let me call this z. So what this is saying, so let me set x prime minus x equals z, which lies in our vector space x, because both of these are in x. This is saying that the norm of z less than delta implies that the norm of t of z is less than m times delta. We can use less than or less than or equal to. Both are fine as definitions. Now, if we put delta equals epsilon over m, then this becomes epsilon. So for whatever value of epsilon we choose, for the value delta equals epsilon divided by m, where m comes from this uniform bound, so we're assuming that this is true, this implies this, which is precisely the definition of continuity at 0.